Structure question from May, June 19, paper 22, question 1. So in this question, we have 1, 2, 4 marks. And the question is about uncertainties. So let's read. A. The diameter D of a cylinder is measured as 0.0125 meter plus minus 1.6%. Calculate the absolute uncertainty in this measurement. When a measurement is presented with a percentage uncertainty, this value here is exactly our delta D over D, which is 1.6%. The question is asking for the absolute uncertainty. So the absolute uncertainty is this value right here. So in order to calculate, we have to rearrange this and make 1.6% times the value of the diameter. So 1.6% is 1.6 divided by 100 times the value of the diameter that was given right here. Now I have my absolute uncertainty. However, to write on this answer, you need to convert to scientific notation. So this is 2. We're going to move the decimal here. So 1, 2, 3, 4 times 10, because you move it to the right, minus 4. So what this value means, if we want to rewrite the diameter measurement in this format, so that will be the value plus minus the absolute uncertainty. So this is D and this is delta D. And now both values, the value of D and its uncertainty in meter. Second question, the cylinder in A stands on a horizontal surface. The pressure P exerted on the surface by the cylinder is given by this formula. The measured weight W on the cylinder is 0.38 Newton plus minus 2.8%. Note that this problem is not to evaluate your knowledge of pressure and the surface area and the force. Is just how you handle the uncertainty, absolute uncertainty, and percentage uncertainty. To calculate the value of pressure, I use this formula and make the substitution for the value of the force, which is 0.38 newtons, and the value of the diameter, which is 0.0125 square. So I'm gonna use my calculator, and 4 times 0.38 equal, divide by, I like to open parentheses here, pi times 0.0125 square equal. This is the mark scheme for this problem, and here is showing the way they want your answer to round to the whole number. So instead of writing this value right here, that should be 33,100 Newton per meter square for pressure. Question B, II. Determine the absolute uncertainty in the value of P. Again, is absolute uncertainty is asking for just the delta P, not the fraction. So usually this is with a unit. So how you are gonna convert all this is very simple. So your delta P over P is equal, now you look at the equation here, so you have the force that is given by W, and plus you always add the fractional uncertainty. So the fractional uncertainty can be a decimal number or can be a percentage uncertainty, which is a fractional uncertainty as well. And I'm going to show you how we do this. So remember, the diameter is a square, so you are going to make the correction right here, because the diameter is going to add uncertainty or error on the value of pressure twice. So that's why you need to make the correction right here, 2 times this. Now, if I want to be working on percentage instead, so everything needs to be in percentage here. So, and that is convenient in this case because all the percentage uncertainty showing for both variables that I need to add here. So for the weight is 2.8%, and for the diameter is 2 times 1.6%. Okay, so now I'm going to write here delta P over P in percentage is equal to, doing my calculation, this is 6%. Okay, but I want my absolute uncertainty. I want this one. So my delta P is 6%, right, times the value of P. So delta P is 6% is 6 over 100 times the value of P is 396.5. I like to use the original value, not the rounded one. So my delta P is, so that's the value of my absolute uncertainty. But because I rounded the mark scheme is rounded this, so they expect they will round this one here, so that will be 190 Newton per meter square instead of this number. If you be asked to write the whole value of pressure plus its uncertainty, so you do this. So the full answer, let's call this way, full answer would be 3100 plus minus 190 Newton per meter square. So that will be, did not ask this question, I'm just adding here so you can see the full, then that will be your pressure value, and this will be the absolute uncertainty for pressure. Question 1 from May-June 20, paper 12, question 4. Readings are made of the current for different voltages across a fixed resistor. The results are plotted on the graph, show the variation of I with V. What is the best description of errors in this reading? I'm going to go ahead and eliminate B. Why? Because the question is asking what is the best description of errors, and B is a contradiction of the question, say neither systematic or random. So I eliminate this question right here. As for options for answer, I need to understand or look for evidence on this graph of systematic error and random error. To do that, the first thing I'm going to do, I'm going to draw a line, the best fit over the values plotted in this graph. And I noticed that absolutely all of them, they are on this line. So this is an evidence of systematic error. So systematic error, they are error caused by the instrument. So if the same instrument or instruments are being used for measuring this value here, so they are going to have the same error, and the results, they are going to be absolutely the same. or you're gonna see the same increments or things like that. Now the evidence of random error will have scattered dots above or below the line, not over the line. So to answer this question, because the graph shows just evidence of the dots on a line after I draw a line of best fit, so you'll be systematic error only. Question number 2 from May-June 20, paper 13, question 5. 2 liquid in glass thermometers in a well-mixed liquid are individually observed by 10 different students. All agree that one thermometer reads 21 degrees Celsius and the other thermometer reads 23 degrees Celsius. And what is a possible explanation for the difference? So let's read each statement and take in consideration what they are saying here. The liquid is not all at the same temperature. I would say this is a contradiction with the story, because the story says that the liquid is well mixed. So that is not possible. All the liquid are in the same container, so it's not possible that the liquid does not have the same temperature. So eliminate it. The readings are not precise. Okay, so precision. So the measuring values are the same or almost the same. And since all 10 students, they have the same measurement, so this is not correct. I want to state this again. So since all students, they took the same measurements, so all measurements, the values are the same, so these measurements are precise. And the statements say the reading are not precise, so this one is eliminated. C, there is a random error affecting the reading. Random error are caused by the observer, the experimenter. Here is also a contradiction with the story, because it say that all 10 students agree with the measurements. So there is no mistake here, no human mistake, no random error. How you say by a process of elimination, this should be the correct one, but let's do the right thing and read, all right? So there is a systematic error affecting the reading. It's very possible, because could be that one thermometer is not set up right, there is a calibration problem, or the liquid in the thermometer is not that sensitive to the change in temperature. So definitely D is the correct answer. Question 3 from October-November 2018, paper 13, question 5. The width of a table is measured as 50.3 plus minus 0.1 centimeters. So this is the value, and this is the absolute uncertainty. Its length is measured as 1.4 plus minus 0.01 meter. What is the area of the table and its absolute uncertainty? Number 1, pay attention on the units. All units here are in square meter, and we have one value in meter and one value in centimeter. First, calculate the area. Area is width times length. Now remember that because this is centimeter, 50.3 you divide by 100 to convert to meter, times 1.40, that's the value for length, and you multiply all these, multiply also the units, so that's why you ended up with square meter, and that's the value of area. And when you look options, so we kind of are in the right track. So to select the right answer, you need to determine the absolute uncertainty for area. So the first step is to calculate the fractional uncertainty of all the variables that are involved in the formula of area. So is the fractional uncertainty for width and fractional uncertainty for length. So here we have, for width, we have 0.1 over 50.3. And I'm going to stop right here. A lot of students ask, why you did not convert to meter? Well, because we are dividing also the units. You are going to cancel the units. This value has no units. Even if you convert, you have the same value here when you divide both numbers. So that's why you don't have to convert in this case. So plus the length is 0.01 over 1.4. So the result of this is 0.009, no units. To add the unit to the absolute uncertainty, so you just need to multiply the value of A, which is 0.7042 square meter, by its fractional uncertainty here. So now our absolute uncertainty is equal to 0.006 square meter. So my final answer with the value plus minus the absolute uncertainty is presented here. So I need to find one answer that matches with that. And right here we have our C option. So that's the right answer. Question 4, May-June 2010, paper 12, question 3. A student finds the density of a liquid by measuring its mass and its volume. The following is a summary of his measurements. Mass of an empty beaker, 20 plus minus 1 grams. Mass of the beaker plus liquid is 70 plus minus 1 grams. And the volume of liquid is 10 plus minus 0.6 cubic centimeters. He correctly calculates the density of the liquid as 5 grams per cubic centimeter. What is the uncertainty of this value? First, calculate the density. So the density is the mass of the liquid divided by the volume of the liquid. The mass of the liquid will be we need to subtract the mass of the beaker. So it's 50 grams. Now remember, when adding or subtracting values with uncertainty, you do your operation to find the value. In this case, you need to subtract, and you need to add the uncertainty. So they add the uncertainty for the beaker plus liquid with the uncertainty of the empty beaker. So you need to add both, which means that the mass of the liquid is 50 plus minus 2 grams. So that is how we have for the mass of the liquid. So going back to density, to find density, so is right here, is the mass of the liquid, which is 50 grams, over the volume of the liquid, which is 10 cubic centimeters. So the result is 5 grams per cubic centimeter. However, the problem is asking the uncertainty of the density. So first, you need to calculate, this is, second, that will be the second step. The first step was to find the value of D, which is this one. Now the second step is to find the fractional uncertainty for D, for the density. So is the fractional uncertainty for the mass plus the fractional uncertainty for the volume. So the mass, we already calculate here. So it's 2 over 50 plus the volume is 0.6 over 10. Okay, so we are here, right? So the fractional uncertainty for density is 0.1. We need now to find the absolute uncertainty. Why? The question didn't ask this absolute uncertainty, but because the options, they have a unit, so we need to find, that's the absolute uncertainty, is the uncertainty with a unit. So D is 5 grams per cubic centimeter times this value here. So now we add a unit for this value. So this is the uncertainty for D, or the absolute uncertainty, 0.5 grams per cubic centimeter, which is this answer right here, B. Question number 5 is from May-June 2008, paper 1, question 4. The resistance R of a resistor is determined by measuring the potential difference V across it and the current I in it. The value of R is then calculated using the equation R is V over I. The values measured are V is equal 1 plus minus 0.05 volts and I is 0.5 plus minus 0.01 amps. What is the percentage uncertainty in the value of R? So first start with our fractional uncertainty. The fractional uncertainty for R is equal to the fractional uncertainty for the voltage plus the fractional uncertainty for I. But it's asking in percentage. That's okay. We can solve this without the percentage and add the percentage later. So in this case, for V is right here, so it will be 0.05 over 1 plus, and I is 0.01 over 0.5. So both values no unit. So my result is 0.07. So here the question is asking the percentage uncertainty. So as you see, all these results, they don't have a unit. So what you do here, you just times 100%. Okay, that will be the percentage uncertainty for resistance. So that will be 7%. Answer C. Question 6 from May-June 2005. Our oldie one here, paper 1, question 4. In experiment, a radio-controlled car takes 2.5 plus minus 0.05 seconds to travel 40 plus minus 0.1 meter. What is the car's average speed and the uncertainty in this value? Number 1, formula for speed. Hello. Speed is distance over time. So like D over T. There you go. Now we have all these, of course we do. So speed here, the distance is in meter, so this is the value, 40 meter, and the time is 2.5 seconds. So when you divide this, you get 16 meters per second, or like Cambridge like to write 16 meter second minus 1, because seconds is on the denominator. Okay, so we got here the value for speed or velocity. Now we need to calculate the uncertainty, and as you see the answers, so we have all the uncertainties, they have units too. So in this case, you need to find the absolute uncertainty, which means that's for speed. The absolute uncertainty, you need to find first the fractional one. So that is the, let's say, the fractional uncertainty for distance plus fractional uncertainty for time. For distance is 0.1 over 40, right here, 0.1 over 40, plus 0.05 over 2.5. That's for time, 0.05 over 2.5. So the fractional uncertainty for speed is 0.0225. No units. To add the unit, what you do is you just multiply this value here, the 0.0225, by the value of the speed that we calculate. Oops, I'm kind of run out of space here. Let me do that. And it's 16. Great. So my absolute uncertainty for speed is 0.36 meters per second, because here we have meters per second, right? So we multiply units with this value. That's what you get. All right, so our final answer is the speed plus minus its uncertainty. So the speed is 16 plus minus uncertainty 0.36 meters. Let's do this. That's the same thing, is meters per second as meter s minus 1. Okay, so now let's try to match this answer with one of the options that we see. All right, so let's, what do you see here? We see, okay, so we see 16. I see 16, probably all of them, but the uncertainty is the one that is going to determine the answer. This is 0.36. I have here 0.36. However, the way that they place here, these two kind of confusing, those two here, but that's okay. We can work this out. So here we have 16.00 and 0.36. So even though the value is the same, but the way that it's presented, these we have 1, 2, 3 significant figures, and here you have 1, 2, 3, 4 significant figures. That's okay. Here we have 2 decimal places. However, that's the trick part, because the value of the speed is kind of whole number. You need to present the absolute uncertainty as a whole number as well, kind of. So you need to round these to 4, and that will be the right answer right here. C. Easy question for a change. So question 8 from October-November 2007, paper 1, question 4. A series of measurements of the acceleration of free fall g is shown in the table. Which set of results is precise but not accurate? Number 1, you need to remember that acceleration of free fall g is 9.8 meter second minus the square, meters per second square. So this is the unit right here. So the question is asking which results is precise, the set is precise but not accurate. Let's eliminate the accurate one. I already went ahead and did, but let me explain to you what I did. So accurate values are close to the real value. So the first row, all they are kind of close to the real value. So that's why I eliminate, because they don't want an answer be accurate. They just want to be precise. Precise values are close to each other. So then I look each one, they are kind of close to each other. I have 9, 10, no, I don't think so, because I have 9, 10, and then I have 8, no, this is not. This is, I have 945, and then I have 899. Let's see the last one, 0.45, 46, 50. Okay, definitely they are close to each other, but they are not close to the real value, which is 9.8. So this is precise, but not accurate. Another easy one. Question 9 from October-November 2018, paper 13, question 4. An ammeter is calibrated so it shows a full scale deflection when it measures a current of 2 amps. The diagram shows the display of this ammeter when it measures a current. What is the current in the ammeter measuring? Let me restate my question. Which current is the ammeter measuring? Okay, so the story is saying that this ammeter is calibrated. Somehow the full deflection is gonna show right here 2 amps. Now I have, how many divisions I have here? 1, 2, 3, 4, 5 divisions. So 2 amps divided by 5 divisions. Each division corresponds to 0.4 amps. So the pointer is right here, so that is the first division 0.4, 0.8, 1.2, because 0.4 here is 0.4, 0.4, 0.4. So up here I have 1.2 amps. Now if this here, this just one division is 0.4, half is 0.2. And half of a half, I have it right here 0.1. So when I add all together, 3 times 0.4 amps up to here, and then I have 0.2 amps plus half of these 0.1 amps. So my total is 1.5 amps. B. Okay, last question. Question 10. From May-June 2014, paper 11, question number 4. An experiment is carried out to measure the resistance of a wire. The current in the wire is this one in amps, and the potential difference across the wire is this one in volts. What is the resistance of the wire and its uncertainty? So if you don't remember the formula for resistance in terms of voltage and current, question 5 on your same test is showing the formula right here in front of you. Okay, so voltage is 8, current is 1, so the resistance is 8 ohms. Now we need to find the fractional uncertainty first. So that will be the fractional uncertainty for voltage and the fractional uncertainty for current. So now we have this is for voltage is 0.4 over 8, and for current is 0.2 over 1. And this is 0.25, no units. We need to add units on this. So our fractional uncertainty for resistance is 0.25. So to add the unit, and that is the absolute uncertainty, is 0.25 times R. So it's 0.25 times 8. So my absolute uncertainty is 0.25 times 8, which is 2 ohms. So my final answer is R plus delta R, the value of R plus its uncertainty. So R is 8 plus minus, this is 2 ohms. And I have a winner here, is D. And that's the end of the test. Structure question from May, June.